Well, we are going to talk about a little different application today, and then we're going to use that some next week. The application today is used on limits, which we haven't actually really gone in depth. We've been kind of using them in the sense that, integrals are just limits as we make things smaller and smaller and smaller, and derivatives are the limit as we approach one point and take the slope of that. So we've been sort of using limits by using derivatives and integrals, but not like explicitly using limits in that sense. But we're going to kind of go back to that today because we will need that in what we're going to set up for next week. And so today we're going to talk about some indeterminate forms of limits and how we can solve those. And we're going to use what's called L'Hopital's rule. It's French, and in your notes I put a link in there, so if you really want to know what the actual pronunciation of that is, you can go ahead and click on that and you can listen to that too, so you can get the pronunciation of it down. Because when you look at the name, it does look like La Hospital. That's not what it is. It's L'Hôpital. But it's a rule, it's a way that we can use derivatives in limits, which is kind of backwards because we use limits to actually build up derivatives. And now we're going to use derivatives to help us solve some limits, right? We don't have to always use this stuff. But when L'Hopital's rule comes into place is whenever you're trying to do a limit, again, that's when a number is approaching some value, and we get something like 0 over 0, or possibly, infinity over infinity, and that can be positive or negative, right? And we've dealt with some of this before, way back beginning of the year. We did some of these like this where we kind of had to manipulate the fraction around a little bit and do some extra little dividing so that we made sure that stuff kind of canceled off. But now we'll be able to solve a whole lot more of those things here. And so what L'Hopital's rule is, here I'm going to show it to you first, and then we'll go through some examples. So L'Hopital's rule has two parts to it. Number one, this part must happen first. Some people skip right over this first part, and then they go on some weird long thing, myself included. Sometimes I forget to do this first part, and I start doing the second part and go, oh, that's why I was wrong. You have to have the first part happen first, okay? Is that you have to check your limit, okay? And we check the limit, and it's working with fraction. We always have to have fraction. We plug in the number, and we see what we get. If you get infinity over infinity, or you get 0 over 0, then you can use L'Hopital's rule. If you do not get this, infinity over infinity or 0 over 0, you can't use L'Hopital's rule. That's the big takeaway, right? If you do not get these first two things, you cannot use L'Hopital's rule. So if you do have those, though, what can we do with this? L'Hopital's rule says we can take our limit of our function, and that is going to be equal to the limit of the derivative of the top and derivative of the bottom. It's a little bit weird to get used to here. A little bit weird because we're just doing the derivative of the numerator and then the derivative of the denominator and sticking them right back in there. It is not a replacement for the quotient rule. Okay, this does not replace the quotient rule. So again, that can sometimes be confusing, and sometimes we can kind of forget about that and be like, because this is a lot easier to do, and we sometimes forget about the quotient rule. We are not doing the derivative of the entire fraction. Then we would have to use the quotient rule. We are just doing the derivative of the top stuff and then the derivative of the bottom stuff and then replacing it. We can only do that if our limit comes out to be this form. And that's what we're going to be going over today. Okay. So to show you guys, excuse me, a little more concrete example on this, this would be something that you would get the form of 0 over 0. So if we take a look here and we try to plug this in, we try to plug in 0, right? We're going to let x become 0. And we're going to see what we get. We plug it into the top. We get either the 0, which is 1, minus 1, numerator 0, which isn't so bad, right? If the denominator is something else, we could have 0 divided by something. But we can see we'd have 0 divided by 0. So that's not going to work out in this case. So then what we did that. We found that it's 0 over 0. And then what we're going to do is we are going to use our L'Hopital's rule. And what that says is we should then have the limit, right? The limit's going to stay the same. We're still going to make x go to 0. That's going to be the same. So let me take a look here and do the derivative of the top part, which is actually not too bad, right? That'll just be 2 times, oops, let's move out of here, 2 times e to the 2x. That's the derivative of the top. And then we do divided by the derivative of the bottom, which is just 1. Okay, so we take here, we do the derivative here, and we would divide that and get 1 in that case. Okay, so that's after applying L'Hopital's rule. That's what we get here. And now what we do after doing L'Hopital's rule, we try and plug it in again, see what we get. And in this case, when we plug this in again, e to the 0 is 1. So we have 2 times 1 divided by 2, which ends up being 2, because we can evaluate that right away. And if you're, maybe we're going through this stuff, especially when I'm going through and checking my stuff, I want to make sure, hey, did I get this thing right? Or did I just make up a bunch of junk and happen to work out? So what I would do is I would take this original function, and I went to Desmos, and I just typed this equation in here. These other ones we're going to be taking a look at here in a second. And so we're saying, hey, what is this as we approach 0? So I kind of follow my graph and see what is it when we approach 0. And sure enough, right here at 0, it's undefined. There's no point there. But we can see it's getting closer and closer to 2 from both directions, which is in fact what we got here, right? It should be at about a height of 2 in there. So that's if you have 0 over 0. Same thing. Here's a second example. Oops. Second example, if we have infinity over infinity, which that's what this is. Limit as x goes to infinity. In other words, we're letting x get really, really large, right? And then we're, seeing where does the graph approach. Okay, in this case, natural log of infinity is infinity. Natural log keeps growing forever and ever and ever. So does x, right? The denominator. So we got infinity over infinity here. So then what I'm going to do in order to evaluate that is we're still going to let x go to infinity, right? Oh, not that. That's not infinity. Infinity. And then we have this part. Well, we do the derivative of the top part. So the derivative of natural log of x is 1 over x, right? That's what that is. And then this is over, well, the derivative of the bottom is 1. So it's all of this stuff, again, divided by 1. It looks a little weird. I'm just putting this here for emphasis so we can see, hey, that's where these pieces went. Okay, took this top stuff, became 1 over x, bottom stuff became 1. If you wanted to simplify that a little bit more here and just say this is 1 over x, I don't know why I keep doing that, then that's fine. Okay, you can also do that too, because you can understand, oh yeah, it's 1 over x and then divided by 1. Okay, I get that, right? So that would be that one. And then here we can see, oh, if we let the denominator of a fraction get really, really big, right? 1 over x, if we let that get really, really large, essentially that's going to approach 0, right? That's what that's going to become if we keep letting that denominator get bigger and bigger and bigger. And that was one of our key pieces that we had talked about earlier in the year. We said, hey, the limit as 1 over x to any power actually will become 0. And again, just to double check on that, I'm going to go, if I get out of, move my, you guys can't see that part, but a bunch of options pop up there. So here I would check this one. And of course, it kind of does a weird, it kind of pops up into here and then it starts to slowly come back down. And eventually it's going to decrease and decrease. And we can kind of zoom out and see, yep, this just slowly approaches 0. Right? As we move x larger and larger and larger, the value approaches 0. So that seems to work out as well. That's what we get on that one, right? All right, moving on. So those are the basic forms, 0 over 0, infinity over infinity. But not everything fits that. There are some things that are kind of strange looking that we can force them to become either 0 over 0 or infinity over infinity. We can force them to become that and then use L'Hopital's rule, right? So here are other sorts of forms that we can have. We can have like 0 times infinity. That is what's called indeterminate form. That's what all these are. They're indeterminate because 0 times infinity, you have nothing times everything. What's left, right? I mean, 0 times anything is supposed to be 0, but also you're multiplying it times everything. Like that might affect something, might go a little bit weird. So the idea on this one is what we're going to do is flip over the 0 So then we get infinity over infinity, because if we put, kind of flip that over on the denominator, that's what we'll get there. And then some other ones that we have: 1 to an infinite power, right? 1 to any discrete power or any numerical power, like 1 to the 1000th is still 1. But if you do that enough times, maybe you get something else, right? Infinity is weird and it kind of strangely affects things, right? So in this case, we'd use natural logs to kind of knock that exponent down, and then that turns it into this form, and then we flip it over and we keep going from there. On this one here, if we have like something 0 to an or 0 to a 0 power, or even like 0 to the infinite power is still kind of 0. Well, like 0 to a 0 power, what's that supposed to be? Because 0 times 0 times 0 times 0 times 0 is 0. But anything to the 0 power is supposed to be 1. So what is 0 to the 0 supposed to be? Now, I want to make it very clear. Specifically, 0 to the 0 is just straight up undefined. You can't do it. It's like dividing by 0. This is not possible to do. Okay? It is not possible to have an answer for just this. But since we're taking the limit and we're getting close to 0 to the 0th power, that's what we're evaluating. We're evaluating getting close to that. So just like you can't divide by 0, you also can't take 0 to the 0 power. That's not possible. But we're using limits, so we're getting close to that, and we're saying, okay, what do we approach as we get close to, right? That's the idea in this one, yeah? And so I'm going to show you a few examples on that, and then you guys can go ahead and start on your homework. So example that we're going to do here is 0 times infinity. So if we take a look here and we try to evaluate this limit, if I plug in e to the negative infinity, means we're backing all the way up. E is really large, but when you back all the way up, it's at 0. So this part is 0 times, well, the square root of infinity is still infinity. So it's 0 times infinity. And we kind of say, oh, what are we going to do in there? Well, what we would do with that is either take one of the other. Usually I like to take the 0 thing, but either one of them. And we're just going to put it on the denominator and flip it over, right? We can kind of do that. So we have one of two options here. I'm going to take kind of the easier one, and I'll show you the second one that would still work out. It would just take a little bit longer to go through. So in here, what I'm going to do, instead of having this e to the negative x there, we could throw it onto the denominator. We could say that this is really the square root of x divided by e to the positive x. So we can throw that onto the denominator in that case, right? So once we do that, now we can check and say, oh, we've got infinity over infinity. It's back in that form. And since I have infinity over infinity, now we can use L'Hopital's rule to figure that out. So in here, that's still, we still have this x approaching the same thing, right? That does not change. But now we have our fraction in here. So we take the derivative of the square root of x, right, which is a little bit different. So I'm going to put that on the top here. So that would, we drop the 1/2 power down, right, 1/2, and then it would be x to the negative 1/2. So I'm going to put that in the denominator. That's this part becoming derivative here. And then we have to do the derivative of the bottom, which is e to the x, right? Derivative of e to the x is just derivative of e to the x. Nothing super exciting there. That's what we would have in that part. And then the last thing, here we could kind of clean this up because now it's fraction over fraction over fraction. We would want to clean this up a little bit. So I'm going to get rid of all of this stuff. And we could say, okay, hey, hang on a second. Let's just take this. If we're dividing by e to the x, really we could just put it in the denominator here, right, in that part. Right, that's what that whole thing is equal to. We can go ahead and do that. And then we can take a look here and say, oh, well, hey, that's kind of interesting there. Actually, let's do these two. We'll make it on a different page here so we can have a little more room to work. But, then when you plug in that infinity value, we can see here that, oh, okay, hey, wait a second. If I put infinity on the bottom, this will be 1 divided by infinity. It's a really, really, same thing as what we had before back up here. 1 divided by infinity, we should get 0. So this whole thing here should end up approaching 0. That's what this should be. So we can say, okay, that goes to 0 in that case, right? That's what that does. And we can go back and check that. Again, I would take my original equation here. Okay. Actually, let's go back. We'll take our original equation even right here. So there's my original equation. I would graph that, and you see it kind of jumps up, or tries to. The exponential tries to take over, but then it quickly, it quickly becomes 0 in there, right? So as we go towards infinity, the graph becomes 0, or the height of that graph becomes 0. And that's what we see there. So I'm going to remove that. Yep, and that becomes 0. Another form that the other two that we're going to talk about, okay, so that was just this form. Our next form is going to be, what if we have 1 to the infinite power, right? How do we do that? So in here, we could look at this and say, okay, well, we got a limit. We got 1 plus 1 over x, the x. So if we try to let this be infinity, this part's going to be 0, and we're going to have 1 to an infinite power, right? And it's not going to be 1 necessarily, right? It might be 1, but we can't be quite sure because there's always this little bit of extra stuff there, right? It's 1 point something to some really big number. So it might not just be 1, right? It might be something else, right? We're seeing, what does it approach to? So the idea on this, when we have, 1 to infinite, or 0 to the 0 power, is we're going to use natural logarithms in order to help us out with that, right? That's what we're going to do here. So let's edit this equation here. So the idea here is, what we would do is we would, instead of writing this whole limit, I'm going to use capital L to represent this limit, so I don't have to rewrite all of this stuff over and over and over again. And then the idea is, we'll take the natural log of both sides, right? We'll take the natural log of both sides of this. Let's see if we can actually get this thing to be a little bit better with its parentheses around here. Okay. So what we'd want to do is take the natural log of both sides of here. So in this side here, I would take, the natural log of the L, and then we take the natural log of this, which is nice because we can always move a limit outside of the natural logarithm, right? So now we would do the natural log, and I'm going to make it of all of this stuff, right? That's what I'm going to do. It looks a little bit funky, but that's our idea. We're going to take the natural log of both sides in there. And what that allows us to do is, this exponent can now drop down in front, right? We can drop this exponent down in front here. And that's what we're going to do in that case. So in here, when we drop that exponent down, okay, so now again, I'm going to kind of forget about this part because we don't need that. We take this exponent out, all right? We can take that exponent and drop it in front of the natural logarithm. And that's what we have here. So we're going to start on a new page on this one, just so we can see that. Now, if I try to evaluate this, we would have infinity here. And then we'd have the natural log of 1. And the natural log of 1, if you want to double check it on your calculator, or you can think about, well, let's just e to some power equals 1. This has got to be 0. So this part is of the form, right, infinity times 1, right? Or yeah, infinity times, infinity times 0, excuse me. So this is back towards this other type that we had talked about, right? And one way to do that is to take one of them and try and flip them over to become something else, right? That's what we can do here. So back in our equation on this one, what I'm going to do is, I know I said take this thing, flip it over. You can flip over either one of them, whichever one makes more sense. So I'm actually going to take this and delete it, right? And I'm going to take this part and say, well, we'll put this over 1 over x, right? Because that should really be the same thing. I mean, it seems kind of weird, right? I took this x and made it 1 over x, but on the denominator. So technically, they're still the same equation. But what this allows now is this top part, the numerator, becomes 0, and the denominator also becomes 0, right? So now we can use L'Hopital's rule here to go ahead and evaluate this function. And now it's going to look a little bit messy. I'm not going to lie about that. So we're going to use L'Hopital's rule here. So I've got to do the derivative of this top stuff. Okay? So derivative of this top stuff is going to be, let's get rid of this. It's going to be 1 over that stuff. So 1 over 1 plus x, 1 plus 1 over x. And then we got a chain rule. We got to go inside and do the derivative of this interior, which is going to be derivative of this part, which is to drop the power down. So it's going to be times -1 over 2x squared. Whew. Whew. A little bit crazy right there. And then what we have to do here, let's see if we can get down, is we got to do the derivative of this bottom part. And the derivative of this, well, we kind of actually just did it. The derivative of this is to drop the 1 down and, whoops, sorry, we didn't actually need that 2 there. But, and let me go up and fix that. Yeah, we don't need that 2. I was thinking too much with those square roots, wasn't I? But the derivative here, drop the -1 down, decrease the power by 1 down to -2. So it looks ugly, right? This thing looks ugly. But if we look closely here, these two are actually exactly the same thing. We can take this and cancel these parts out. So that's what I'm going to do with a nice red line to make me feel good about myself, right? Is we'll just cancel that part out. Yeah, bam, that stuff's gone. And so all we have left, so I'm just going to get rid of that guy. And let's go all the way down to the bottom here. We can get rid of this equation. Hoo-hoo-hoo. There we go, right? Now we can just do this limit, right? Which is a whole lot easier because this is 1 over 1 plus 0, right? That's all this thing is 0 here. So it's really just 1 divided by 1, which is 1, right? Fairly kind of almost seeming uneventful in that amount that it just becomes 1. It's like, oh man. But, and we can again just go back and double check that that's what this thing runs into here, right? Because if we check that that's what this is, we would say, okay, it should become 1. So I'm going to go back here and plug this guy in, and we see that, oh man, we go way over here and it's not 1, right? Here's where 1 is at. It's down here. It starts at 1, and then it jumps way up here. It's going above 2. I mean, almost 2.5. It jumps above 2.5. Doesn't quite get to 3. What in the world's going on? Maybe it does get to 3 eventually. I'm not sure. What happened? Oh, man. Tell you what, remember we evaluated this limit, but what did we do to get here? We took the natural log of it, right? We did that piece. So there's still that final step left. And that's one that I sometimes forget about as well when I'm going through that, is I say, oh, actually, that's not that. That's the natural log of the limit is equal to 1. And so then we have to make sure that we, kind of change that back to exponential form. And that would be just e to the 1 power, right? That's what this would become. We have to make sure that we undo that natural logarithm part as well. And then what we can see here is actually, yeah, in fact, if we check at this height of e, that is exactly what this is approaching, right? As we go towards infinity, it's approaching e. So when you have a 1 to the infinite power, excuse me, we use that natural log to knock the power down, but then we can't forget that, oh, it was a natural logarithm that I had to use. So we have to go back and undo that natural logarithm at the end. Yep. All right. Last example here, going to be very similar, right? Because we have 0 to 0. So to deal with that extra exponent, we're going to take the natural log of this stuff. Okay, that's what we're going to do. So I'm going to grab this thing here, okay, and we'll just call this as our L, and that's what we want to do on this. Okay. So we're going to say L is equal to those types of things. I like to use a capital L because that makes sense to me that that's, that our limit. Okay. And then in here, we would take the natural log of both sides. Okay. And again, natural log can move inside of a limit. So natural log of all of this stuff. Okay. Which would allow us then to take this exponent. We're going to knock that exponent down. And then when we check this, right, when we check what this type of thing is, in here we will have try to plug in 0, we will get 0 times, well, sine of 0 is 1, right? The natural log of 1 is also 0, right? So this one, there's not a whole lot going on. I'm actually going to take this, so we get a little more room so I can sort of explain what's going on there a little bit step by step so we can see how that's working. Again, this part, this x thing here becomes 0, and the sine of 0 is 1, correct? That's what we have there. And then we can figure out that, oh, hey, the natural log of 1, well, we can grab that one, is also 0, right? And so all of that stuff sort of just disappears in that case. We have the limit of 0 of 0, right? That's essentially what we have there. And so all of this becomes 0. Yeah, which then leads us to the fact that our L is equal to e to the 0. We have to undo that, which is in fact just 1. So kind of maybe a little bit of a letdown on that, nothing super exciting there. But it can happen that this whole limit just sort of fizzles out and disappears, right? We really, in this case, didn't have to use LHOP, right? We didn't use L'Hopital's rule. You don't always have to use L'Hopital's rule because in fact here, it just ends up working out. We get 0 times 0. I don't have to do that. I don't have some weird looking fraction there that we have to do. We can get 1. And then we want to go back and double check that. Sine of x to the x power. So let's turn these guys off. Sine of x to the x power is a weird looking guy. It sort of jumps all over the place and it freaks out all kinds of things because you're trying to do weird exponents in here. But the piece that we are concentrating on is what does it kind of get to as we approach 0 from the right? Yeah, I probably should have mentioned that. Again, that's what this means, that we're approaching 0 only from the right-hand side, no other direction. So here we're approaching from the right, and sure enough, that's what it's going towards is 1. Okay, we can't quite get there. If we try to get to 1, oh, actually it does say that. Desmos is a little bit strange in that it will evaluate that. Technically, you couldn't evaluate that, but oh well, computer software sometimes will try that. So here we know that that will become 1 in that case. Yeah. Something to mention though is we don't always have to use L'Hopital's rule. Sometimes we start doing this, right, and it's kind of like the whole, the old analogy that, if you have once you have a hammer, everything starts to look like a nail, right? That's the same thing. Once you have L'Hopital's rule, everything starts to look like infinity over infinity. You just start looking for it and you try to just apply it everywhere. But that doesn't always have to happen, right? If you can just evaluate it like we did, 0 times 0, there's no need for L'Hopital's rule. You don't have to use that. And so that's like in here, I'd put just at the end, these are times like, oh, it kind of feels like we might use L'Hopital's rule, but we don't actually need to use that, right? If you have 1 over infinity, right, kind of like we did in the examples, that's just 0. Like, you're done, right? We don't need to go anymore, or just any number, in fact, over infinity is just 0, right? Like that's all that's going to be. I'm saying if you have some number over 0, that's probably going to explode and become infinity, right? Or positive or negative infinity, depends on the direction, but that's all that's going to become. Or if you have infinity times infinity, that's just really, really big, right? We're taking a big number times another big number. It's just going to get super big, right? The same thing, infinity over a number, just infinity. Or this last one that I have actually made the mistake on myself many a time, is if you get 0, we start doing calculus so much and try to be careful about zeros and infinities that my brain's just on alert for 0 all the time. And I go, oh, 0 divided by 8. Oh man, I need to do calculus. No, we don't. 0 divided by 8 is just 0, right? Don't forget that, right? Those basic rules. Sometimes we get going on all this complex stuff and then forget, oh yeah, there's just this easy stuff in there too. So don't forget about those. You get going so much on this L'Hopital's rule, so much on these derivatives and integrals, that we sometimes forget even just that basic, back in 3rd grade math. 0 divided by 8 is 0. And then you're like, oh yeah, kind of remember that. So you guys have your assignment there. If you do have any questions on that, you guys have been pretty good about sending me emails, asking questions on those things. Continue doing that. And Hopefully everything's going well for you. Talk to you later.